Imagine standing at the edge of the ocean, staring into the blue abyss. You've seen the colorful reefs near the surface, teeming with life that feels familiar, almost friendly. But what happens when you go deeper? Why do the creatures down there begin to look like they've stepped out of a nightmare, or is what we're seeing actually a masterpiece of survival? Today, we're diving into the deep sea to uncover why animals get weirder the deeper you go, not just in how they look, but in how they function. This is a journey driven by questions, where every answer reveals another mystery waiting below. Ready to descend? So, if you're curious about the ocean's hidden worlds, hit that like button and subscribe for more explorations like this. Let's keep the adventure going. We start our descent in the sunlit zone, also known as the epipelagic layer, stretching from the surface down to about 200 meters. Here, sunlight floods the water, powering photosynthesis and supporting a dense, energetic food web. Fish have sharp vision tuned to a full spectrum of colors and bodies built for speed, agility, and efficiency. This is the ocean we recognize. But it doesn't last long. Below 200 meters, we enter the twilight zone, where light fades rapidly. Only blue and green wavelengths penetrate this far, locking the ocean in a dim, perpetual dusk. So how do creatures survive when vision begins to fail? Why would evolution favor eyes that look almost comically oversized? To answer that, let's meet one of the ocean's true superstars, the lanternfish. These small, silvery fish, often just a few inches long, are among the most abundant vertebrates on the entire planet. Their numbers are staggering. They make up a huge chunk of the deep ocean's biomass, forming massive schools that migrate up and down every day. And their eyes? They're enormous relative to their body size, huge bulging orbs that dominate their little heads. Why so big? Because in this faint twilight, every photon counts. These eyes are packed with rod cells, the ultra-sensitive detectors tuned specifically to the dimmest traces of blue-green light filtering from above. Their eyes can gather and amplify light in ways our own eyes could never match, up to 100 times more sensitive to faint backgrounds. It's like having built-in night vision goggles that spot the tiniest flicker from miles away in our terms. But even that incredible vision isn't always enough in such a shadowy realm. What if you could make your own light? Enter bioluminescence, nature's built-in flashlight. Around 90% of deep-sea animals can produce light through chemical reactions inside their bodies. But what problem does that solve in a place where being seen often means being eaten? For lanternfish, this glow isn't for attracting attention, it's for hiding. By glowing from their bellies, they match the faint light filtering down from above, erasing their silhouette from predators below. This is counter-illumination. As we sink deeper, past 500 meters, the questions intensify. How do you hunt when light is almost non-existent? The dragonfish offers a clever answer. Red bioluminescence. Red light is absorbed quickly in water, meaning most deep-sea creatures can't see it at all. But dragonfish have evolved specialized pigments that allow them to see their own red glow. To everyone else, the ocean remains dark. To the dragonfish, prey is illuminated. It's like carrying a private spotlight no one else knows exists. And to stay hidden while using its own light, it has evolved ultra-black skin. Certain species, like the Pacific black dragon, absorb over 99.5% of incoming light thanks to dense layers of melanin-packed melanosomes that trap photons. Even its bioluminescent flashes, or the glow from recently swallowed prey, are absorbed rather than reflected, preventing the animal from becoming a visible beacon. Why evolve such perfect darkness? because in a place where any stray glimmer can give you away, total absorption is the ultimate camouflage. Other animals take a different path: transparency. The glass squid's body is nearly invisible, allowing light to pass straight through it, no clear outline, so predators struggle to detect it at all. And then there's red, nature's invisibility cloak. Since red light doesn't penetrate these depths, animals with red pigmentation appear dark or black to most deep-sea predators and prey, blending seamlessly into the abyss. The bloody belly comb jelly is a stunning example. Its crimson belly masks glowing prey in its gut, so a recent meal doesn't light it up like a beacon for hunters. But this isn't rare. Red camouflage is widespread down here. Many deep-sea fish, like certain hatchetfish or stoplight loosejaw, sport reddish hues that render them nearly invisible under dim blue light. Giant red jellyfish, such as the phantom jelly, drift like ghosts, their reddish-brown bodies vanishing in the dark. Even some ctenophores and midwater crustaceans rely on this trick. Why is it so common? Because when your world is endless black, wearing red is like wearing nothing at all, perfect stealth in a realm where being seen is death. Drop past 1,000 meters into the midnight zone, and sunlight disappears entirely. The darkness is absolute. Pressure reaches up to 100 times that at the surface, temperatures hover near freezing, and plants vanish completely. No photosynthesis, no green life. So how does anything survive? The answer drifts down from above. The deep sea is fed by marine snow, a slow, steady rain of organic debris. Dead plankton, fecal matter, mucus, and fragments of once living things gently fall from the upper layers, accumulating in the darkness below. It isn't much, but it's constant. This drifting snowfall feeds everything from filter feeders to scavengers. Because food is scarce and unpredictable, many deep-sea animals evolve slow metabolisms, expandable stomachs, and a simple rule: when food appears, take it, no matter how big it is. But that's not all. And this is the mind-blowing part. When you dig deeper, you will then realize that camouflage isn't the only adaptation. Behavior changes too. Consider the vampire squid. Neither squid nor vampire, but a relic from ancient oceans. It drifts slowly through the water, feeding on marine snow using sticky filaments. When threatened, it doesn't flee. Instead, it flips itself inside out, exposing spiny xeri, and releases clouds of glowing mucus as a decoy. Why such dramatic defenses? Because in the deep sea, energy is precious. Sprinting away isn't an option when food is scarce and metabolism runs slow. Deeper still, around 2,000 meters, vision becomes increasingly useless. So why keep eyes at all? Many species reduce them or lose them entirely, redirecting energy toward other senses. But what replaces sight? The answer might question everything you know about the ocean. First, the lateral line system, a system used in almost every fish in the deep sea. A network of sensory canals and pores running along the body like an invisible radar for water movement. In the deep sea, these canals often widen or feature extra superficial neuromasts, tiny hair cell detectors to boost sensitivity in the quiet, low-noise environment. They pick up the faintest hydrodynamic disturbances, the subtle wake of a passing animal, water currents, or even the pressure wave from a distant predator. Imagine drifting blind, yet feeling every ripple in the water column. This is how many deep-sea fish detect prey or avoid threats without a single photon. Then there's electroreception, a true superpower in species like the gulper eel. These eels have specialized gel-filled pores that detect the tiny electric fields generated by every living muscle contraction or nerve impulse. Prey can't hide their bioelectric heartbeat, So even in pitch black, the gulper senses the faint electrical twitch of a shrimp or fish nearby. It's like passive radar. No energy spent generating signals, just tuning into the electric whispers of life. And don't forget chemoreception, effectively smelling or tasting the water itself. Many deep-sea animals rely heavily on enlarged olfactory organs, nostrils, rosettes packed with receptor cells, to detect dissolved chemical traces over vast distances. Food odors, pheromones from mates, or alarm cues from injured prey drift far in the slow currents. Scents travel farther and linger longer than light ever could in the abyss. Why evolve these? Because in endless darkness and scarcity, sound and chemical signals become the longest-range senses available. These adaptations turn the deep into a sensory landscape we can barely imagine, one where animals see with their skin, electricity, and chemistry. If survival is strange down here, reproduction is even stranger. Finding a mate in the vast, dark ocean is like searching for a needle in a planetary-sized haystack. So why does evolution sometimes lead to parasitic mating? The anglerfish provides the answer. Females are the large, fearsome predators we recognize, complete with bioluminescent lures used to attract prey. Males, on the other hand, are tiny, almost larval, and equipped with oversized olfactory organs to track down a female. When a male finally finds one, he bites and never lets go. Over time, his tissues fuse with hers, skin, blood vessels, everything, until he becomes a permanent, living sperm supply. In some species, multiple males attach to a single female. Disturbing? Absolutely. But in an environment where encounters are incredibly rare, it guarantees reproduction. It's evolutionary insurance against extinction. As we approach the abyssal plains around 4,000 meters, survival becomes even more specialized. Scavenging dominates. When a whale carcass sinks to the seafloor, it becomes a temporary oasis of life. Hagfish swarm in, tying themselves in knots to tear flesh free. Bone-eating worms dissolve skeletons using acid, hosting bacteria that break down fats locked inside the bones. Why such specialization? Because marine snow alone isn't always enough. These rare feasts can sustain entire communities for decades. Descend further into the Hadal trenches, beyond 6,000 meters, and extremes reach their peak. Snailfish, soft-bodied and gelatinous, thrive under pressures that would crush most life, thanks to reinforced cellular structures. At hydrothermal vents, superheated, toxic water pours from the seafloor. Tube worms here have no digestive system at all. Instead, they farm bacteria inside their bodies that convert chemicals into energy through chemosynthesis. Why here, in conditions that seem utterly hostile? Because life adapts, turning poison into opportunity. Every strange feature we've seen, glowing lures, fused mates, invisible bodies, follows a clear logic. The deep sea is a world of darkness, pressure, and scarcity. Evolution responds with efficiency. Ultra-sensitive eyes in dim twilight, logical. Transparency and ultra-black skin, perfect camouflage. Bioluminescence, a multi-purpose survival tool. Parasitic mating, guaranteed reproduction. Sensory swaps, adapting to what actually works. Nothing here is random. It's all problem-solving under extreme conditions. But one question lingers. If weirdness increases with depth, does it stop at shape and behavior? Or does it affect size too? Why do some deep-sea animals become enormous, giant squids, colossal isopods, while others shrink? If you're curious to find out, check out our previous video, where we go deeper into deep-sea gigantism. So if this journey sparked your curiosity, like and subscribe to join the next one. Thanks for exploring the depths with us. We'll see you down there.